So hello everyone, we are MorphMind, apparently. We're going to be talking about mechanical neural networks. So why would you want a mechanical neural network? Well, as we all learned yesterday, computing in space is quite challenging because computers are not immune to radiation or bit flips, so you need either very expensive computers or you need redundant systems. Now, one quite popular form of computation that's emerged, I suppose, recently is neural networks. For those of you who don't know how a neural network functions, it essentially relies on very simple non-linear functions, and the key here is that it's non-linear. Now, we also know that mechanical structures can have non-linear behaviors. So there's an argument that you could reproduce the activation functions, the non-linear activation functions of the neural networks using mechanical structures. And you might wonder why you'd want to do that. Well, there's an argument that if you could successfully make a purely mechanical neural network and you could scale it down, then even with quite a low amount of neurons, you could have enough computational power to essentially make smart sensors. And one of the advantages of this is that you can use the input of the sensor directly as the input of your neural network because it's purely mechanical. There's also advantages in terms of low power consumption, so for long duration missions that take place far away from the sun. There's advantages in terms of high radiation environments because the system is now immune to bit flips. And there's also an argument that if you go the other direction and you scale your structures up, you could have structures, mechanical structures that are capable of learning. So you could adapt its performance based on the challenges that you're facing. So what we decided to do over the course of the last 2 days is essentially provide a proof of concept. So a proof that you can build a very simple mechanical neural network. And to do this, we decided to replicate the performance and the behavior of one of the most widely used nonlinear activation functions, which is the ReLU function. This is the ReLU function. Essentially, it has a flat part in the negative. When the input moves to the negative side, the output remains unchanged, and then you have an activation point where afterwards the output scales directly with the input. So this is how we decided to replicate it mechanically, using a simple spring with the input, with one side position as the input and the other side position as the output. Essentially, we can pull the spring in one direction and the output won't move, so that's our flat part in the negative direction. And we can push the spring and the output will move, and that's our essentially linear part in the positive direction.
So our first prototype was using a flywheel mechanism, which had a problem that the backdrivability between neurons meant that neurons within the same layer were having interactions that shouldn't have been there and were perhaps causing the neural network to be unstable to use. So we used wheels to create a torque advantage. Down here you can see a web simulation that we made, and we changed the radii of the connecting points between each node, we're calling them, to kind of determine their weight.
So the flywheel model had some issues, basically because you'd need to drive down the torque a huge amount for it to no longer be backdrivable, and so your output is now very, very small, and so when you start stacking layers, it no longer really works. So we decided to move to a different concept, which is illustrated slightly small here, and which we've got a prototype of here. And the idea is essentially we've created a theoretically non-backdrivable linear actuation mechanism. So if you push on the input, then the output's going to move, but if you push on the output, then the input won't move. And what this means is that action from one neuron will have no effect on actions of the other neurons in the same layer. And this addresses the scalability issues and was kind of the final mechanical output that we've provided here. So We had some issues because 3D printed plastic has quite a low coefficient of friction, so it still remains somewhat backdrivable. But on a very basic model which we have here, essentially what we have is 2 inputs and 1 output and 2 ReLU functions. And what we've demonstrated mechanically is that you can recreate the behavior of neurons, and you can combine them to create a very simple network.
So to help design our systems, we knew that we wouldn't perhaps be able to practically build the systems in real life, although we did build mini concepts which had a few issues. We used the CAD drawings that Otter made for the 3D printer and imported it into a web application which used several nodes similar to the flywheel system I showed you earlier to connect them all together. And also Dom helped build our neural network in the back end, which fed into these systems, which he's hopefully going to talk about in a second.
Yeah, so why would we want to simulate the physical system? So when we build this thing, it's like it's like static. So we've trained it in the simulation, and then we build it, and it can't then learn. It's doing its job that we trained it to do. So we train the model in the simulation to provide the physical system specs to build a physical model. And obviously with simulations we can make them as scalable as possible. So we just opted in for a simple XOR example. So an XOR is a simple logic gate that has 2 inputs and produces an output. And it only produces an output if only one of the inputs are on. So, if it's both 0, it would be a 0. If it's both 1, it would be a 0 as well. Otherwise, it would be 1. So this is our loss function over time. So you can see we successfully the loss function reaches 0. So we successfully trained our network.
Do you want to demo it now?
Yeah. So if you go onto the
yeah.
So yeah.
Come over.
Oh, good, yeah. So you can see here, this is like the function of the neural network. So you can see when it's 1 and 1, we got a 0, and when it's 0 and 0, we got a 0. But if it's 1 or 0 and 1, then we get a 1. Okay, so then we made this front end here, and you can see here, currently it's a 1 and a 0, and we get a 1 as an output. But if we move this down to a 0, you can see the network adjusting, and it comes out as a 0 for 0 and 0, and then we can move this one all the way up, and we will get a 1. Yeah, and then if we were to move input 1 all the way up, we would go back down to 0. Yeah. So yeah, we successfully replicated the XOR. We probably didn't need this many in the hidden layer, but it looks better with more, so we made more. Yeah, so okay. Yeah, so I just had all the neural network architecture in Python, and we just created an API. So the Python stuff was on my computer, so we used a service called ngrok to expose my local port to the front end, which is what the front end was just showing. So yeah, thank you.
Why an export?
I guess it's probably the most simple example of just a simple example that has that has non-linearity in it.
So the idea is kind of we just wanted to show that it could, using a physical simulation, we could produce actual computation and it's a fairly standard kind of, I suppose, benchmark test to just replicate an XOR data set and to try and model it.
Yeah, we were looking into character recognition as well, but that would have gone up to 728 minutes. And, it was already quite pressed for time, so we held off from that for today.
Yeah. So presumably, if you were to put these on a spacecraft and run them constantly with some mechanical wear on them, is that preferable to the damage radiation would do just a low integration chip running with a comparable network?
Is it preferable?
Yeah, is it the mechanical wear on this device, would that be better than radiation damage? Because you could put a neural net this small on like a very sort of small scale integration chip, so like just to make it more a radiation tolerant chip. So is the mechanical wear going to be worse than radiation?
I mean, in the long term, obviously, it will wear its performance will degrade just as an equivalent computational system would. Its advantages are more kind of in what I was talking about earlier, that it's resilient, it's unpredictable, and you can obviously not with something as bulky as this, but if you were to scale it down using, for example, MEMS, then you can make something that's quite a lot more power generous than the computer.
What would, if you sort of mechanically altered one of those, could you sort of like increase the friction or decrease the friction in one, and still have, how long would it take for the result to degrade and you lose the output? Because presumably if they sort of fail a little bit, hopefully if you train the network well, it could be resilient to losing one or more, or having one or more shift values.
I see what you mean. I don't have the answer in terms of time it would take for the radiation damage to accumulate.
Perhaps Dom, you could answer a bit.
One more question. It's more like a theoretical question. How small, as an estimate, how small do you think you can get each of the mechanical neurons? Or is that kind of too far in the future to give an estimate right now?
I mean, for now, obviously, we've got this huge bulky model. There has been kind of proofs of concept as well using microelectromechanical structures, MEMS, showing that you can, not showing that you can achieve computation, but showing that you can achieve some behaviors of a neuron. And so there's an argument that you can use them to then make systems. In terms of actual size, I can't give you an answer, but I think with all these kind of computing devices, you start out with something very huge and chunky, and then it's more of an optimization problem into running as small as possible.